Okay, so in this video we're going to be talking about electromagnetic induction and coming up with some rules that can make some predictions about how it works. So let's start off by talking about how you actually create a magnetic field, because that's the source of everything that's going on here. So magnetic fields are formed around moving charged particles. So that's going to be key in terms of what's happening here. So what we're going to look at is inducing an EMF in a conductor. So you can see on this diagram, we've got a wire going across here. So before it's moving, you can see that the free charges that are inside your wire are stationary. Therefore, they don't have a magnetic field, so nothing is going to happen because they can't interact with this magnetic field here. Okay, so that's before. So nothing happens because we've got no magnetic field around these electrons. If we start the wire moving, suddenly what we've got are moving charged particles, which will have a magnetic field around them. And that magnetic field can interact with this magnetic field, and that's what the source of electromagnetic induction is. So how do we know which way the electrons are going to move? Well, we're going to be using Fleming's left-hand rule. So what we're going to do is we're actually going to move the conductor downwards in this direction here. So that's the direction the charged particles, these electrons you can see in your wire, are moving. They're moving down. So that's why I'm going to point my middle finger that way. You can see the field is marked by X's, so that's going into the plane of the page. So my first finger is pointing into the screen. So you can see that my thumb is pointing along to the right. So this is the direction of conventional current. And therefore electrons are going to go the opposite way. So that's just using Fleming's left-hand rule that we've already met before. So the wire is moving down, which means all the charged particles are moving down the page. We've got the field into the page, so my thumb is pointing to the right. So what actually happens in the wire is the electrons move to the left, and that leaves this right-hand section positive. So we're not actually moving any positive charges at all. The positive charges are created by the absence of electrons because they've moved to the left. So let's put that in writing. So first of all, what rule are we using? We're using Fleming's left-hand rule, and that predicts that the conventional current would move to the right based on the fact the wire is moving down. So what that then means is the negative electrons are going to go left because they go in the opposite direction for conventional current, and that leaves the right-hand end positive. That's what we're going on. That's why if we move a wire into a magnetic field, we can use a galvanometer and we can actually see an EMF being induced. So what is an EMF? Well, on a battery, for example, which is a typical EMF source, we've got one terminal that's positive, we've got one terminal that's negative. We've got what we call a charge gradient. And we've got exactly the same thing here. We've got one end that's positive, we've got one end that's negative, so we say an EMF has been induced here. Okay. So let's describe the model we actually use to explain electromagnetic induction. So essentially the key idea is you get an EMF or a charge difference, if you like, induced whenever a conductor, and it's actually key, it has to be a conductor. Why? Because we need the free charged particles. So it has to be a conductor, and it cuts through a magnetic field line, also known as the flux line. So just what I mean by that, if we have like a north and a south here, these lines that we draw in between them going from north to south, these are what we call the flux lines in there. That's what we mean by that. So anytime a conductor cuts through one of these lines, there is going to be an EMF induced in that conductor. Okay, so there are a few different scenarios where we can create this happening. So we can make magnetic field lines cut through a conductor. So the first one we've already met. So we actually move the conductor and it cuts through a stationary magnetic field and it induces an EMF in the conductor. That's what we've seen so far. But it doesn't have to be the conductor moving. So we could just do the opposite thing. We could move the magnetic field, have a conductor stationary, and we can induce an EMF that way. So it's essentially the opposite process, but we've still got field lines cutting through conductors. It doesn't matter which one's moving. The last one is a little bit more complicated. So we have an alternating magnetic field cutting through a stationary conductor, and that's what I'm going to dig into in a bit more detail. So how do we create an alternating magnetic field? Well, first of all, we get them around wires that are carrying a current. So this we've seen before, that if we have a current carrying wire, we have a magnetic field going around it, and we can predict which way the field is going using our right-hand corkscrew rule. You can see if we put a right thumb upwards, our fingers tell us we're going to be going, the field is going to go in that direction. So how do we create an alternating magnetic field? Well, we do it using an alternating current. So a current that's constantly changing in magnitude and direction. So what that's going to mean happens is that the field lines are going to be constantly moving, because a large current has a very strong magnetic field, which means the lines will all bunch up together. Or if you have a weak field, the lines get further and further apart. And if our current's changing direction, these field lines are also going to be changing direction. So we've created another scenario where these field lines are moving. So if we put another wire into that field, that wire would have an EMF induced in it. And the faster we alternate that current, the larger the EMF we will induce. So let's actually get a picture of that. A wire with a high current will have these field lines really close together. As the current decreases, what's going to happen is it's going to turn into this one in the middle. So the lines will get further and further apart. And once we have no current, we won't see any field lines at all. Because remember, no current means no moving charges. No moving charges means no magnetic field. Okay, so that's what we have going on when we have an alternating current going through our wire. So what does an alternating current typically look like? Sinusoidal in shape. So this is a very typical alternating current. So what are we going to actually have? So at this point, maximum current means field lines closely packed in here. And then as the current decreases, the field lines move apart. And then here, when it gets to 0, you have no field lines. And then we could continue, so we can get the field lines will start to appear and getting closer and closer together until we get the peak closeness here. But essentially what we're doing is creating a scenario where the flux lines are moving, and that's the key idea. Moving flux lines, if they can cut through a conductor, they can induce an EMF. Okay, so those are our kind of 3 ways of inducing an EMF. Moving conductor, moving magnetic field, alternating magnetic field. Okay, so what I'm going to look at now is something called Faraday's law. So we don't really need to know what Faraday's law is at this level, but we do need to know the key picture from Faraday's law. So I'm going to introduce it to you and then essentially draw out of it what we need to know at this level. So Faraday's law, named after Michael Faraday, says that the magnitude or the size of the induced EMF is equal to the rate of change of flux linkage. Now that all sounds a bit like gibberish at this stage. So what does this term that we've got at the end, flux linkage, actually mean? So flux linkage is just a way of describing the flux lines that are currently passing through your coil or through your conductor. So there'll be lots of magnetic field lines around your magnet. Not all of them will be interacting with your conductor. So we use the term flux linkage to identify the ones that are actually cutting through our conductor. It's just a fancy way of saying that. So what is this law really saying? It really says that the more charged particles that cut through magnetic field lines per second, the higher the induced EMF. So where is this per second come from? Well, you'll notice in here it's got this word rate. Rate means per second. So essentially, the more charged particles that can cut through magnetic field lines per second, the bigger the EMF we're going to induce. And that's what we need to know at this level. So how can we create this scenario? Well, we can use a stronger magnetic field lines. What does that mean? It means the field lines are much closer together, or another way of expressing that is there are more flux lines per unit area. So when our conductor moves through, it will interact with more field lines. That kind of makes sense, hopefully. We could also move the conductor faster, because that would mean the conductor cuts more flux lines per second. Hopefully that makes sense too. And the third thing we can do is move a higher number of series conductors through. Because that's going to mean if you have more conductors, that's more charged particles that are cutting through per second. So what does that really look like? Well, we don't really see conductors connected end to end. What we're going to see there is a coil of wire, and we'll wrap more coils around, and that will mean there's more conductor moving through per second. Okay, so those are our three ways of creating a larger EMF, essentially. See that with the example that we met earlier. So again, remember we said the conductor was moving in this direction, and we've got the field into the page. So with my right hand, my first finger is pointing into the plane of my screen. Your thumb is pointing down because that's the direction of conductor motion. So you can see that, as before, conventional current goes in this way. So therefore, electron flow goes in this direction. And you'll notice that the right-hand rule makes exactly the same predictions that the left-hand rule did earlier. I think we just try to separate the rules. So with the left-hand law, we use it specifically for the motor effect, for forces on charged particles. The right-hand rule, we use it always for induction. It helps us separate the two rules. So that's why we have these two rules, but they both make the same predictions about what will happen.